Okay, Emma, whenever you're ready.
Okay, thanks, Andrew. Yeah, I wasn't able to speak this morning, so thanks for being flexible, letting me go this afternoon. Hopefully there's some people listening who are still interested in planetary atmospheres. Right, so I'll get started. My name is Emma Dahl. I'm a fifth year graduate student, PhD candidate at New Mexico State University. I'm working with Nancy Shanover and Glenn Orton, basically on observing and modeling Jupiter's atmosphere in support of the Juno mission. So my PhD project is kind of split into two big chunks. The first has everything to do with collecting the data, calibrating it, and the second is actually using the data and modeling. So I've split my slides respectively. So to start with the instrumentation, observations, and data reduction, here at NMSU, we built this instrument called the NMSU Acoustic Optic Imaging Camera, or NAIC. We built and characterized it with some NMSU engineers here, and there's a top-down picture of it. It's a unique instrument that uses something called an acoustic optic tunable filter crystal as the filtering element. If you're interested in electronics and optics and stuff, please talk to me afterwards about how they work. They're really cool. Basically, we step through wavelengths with the AOTF and then image the science object with the CCD. That's basically how it works. And then we use NAIC with a 3.5 meter telescope at Apache Point Observatory here in southern New Mexico. There's a picture of it mounted to the telescope in the big silver box. And we basically go observe Jupiter whenever the Juno spacecraft completes these close perijove passes of the planet, and those happen about every 2 months. So to date, we've completed 12, I think maybe 13, I lose track at this point, observing runs. And the result of all of those are these hyperspectral image cubes of Jupiter taken in conjunction with Juno passes from 470 to 950 nanometers. So we really cover that visible wavelength regime where we're sensitive to the color and the structure of the uppermost cloud deck of Jupiter's atmosphere. So it's a very highly complementary data set to what Juno's measuring. So in order to get those data ready to use, we have to process them. And I've written a data reduction pipeline in Python to take an unprocessed image there on the left, and then it makes a nice little neat hyperspectral image cube that's all reduced and calibrated. There's some example wavelengths there on the right. And you can find my pipeline on GitHub. I think it's mostly up at this point. Yeah, so you can go to the next slide, Andrew. So the next part of my project is actually using the data, the radiative transfer modeling. So the big picture questions that I'm using these data that we've collected to answer are, what is the structure of Jupiter's uppermost cloud deck during the Juno era? And we want to know also what makes Juno's bands and storms red. That's still a really big, outstanding question in the Jovian community. We don't know what makes the great red spot red, basically. So in order to help answer those questions, I'm currently using the Nemesis radiative transfer code to test the hypothesis of something called the creme brulee model of Jupiter's clouds. So it's basically just what it sounds like. It's a parameterization of the clouds. It says there is a thick tropospheric cloud with a very thin coloring agent, kind of like a crust on top of the cloud layer. So there's two bodies of work, one that says that's not a very good model and the other says it is. And so we're kind of testing to see which of those it might be. So in order to test this, we've extracted spectra from our Jupiter cubes. And so here's an image of Jupiter with the locations of the cubes that we've extracted with those little colored squares. So we've pulled spectra from the north and south equatorial belt, those bands on Jupiter, and the equatorial zone in the middle there. And then the plot at the bottom is the basically the results I have at this point. So thanks Andrew. Let's see, the solid lines are the data, the dashed lines are the models. So you can see that they're pretty closely matched at this point. So far the creme brulee model is a pretty good fit to our spectra. So we're writing this up right now in a paper. Dahl et al. 2020 is in prep, and that's not a soft in prep. We're almost done, or we're almost ready to submit it. And then, as I mentioned earlier too, there's a lot more work that we can do with these data. A lot of complementary studies that we can do in order to provide context for Juno measurements in deeper parts of the atmosphere. You can go to the next slide. And that's basically everything. Here's all my contact info. I'm interested in, instrumentation, modeling, mission planning, gas giant atmospheres, kind of a big plethora of stuff. So please get a hold of me or take a look at my GitHub page if you're interested in any of my work. Thank you for your time.
Okay, up next, Vishal.
Hello, right.
There you are.
Hello.
Hey, whenever you're ready.
All right, thank you, Andrew. Hello, I'm Vishal Singh. I'm a final year PhD candidate at Arizona State, though I spend most of my time developing and running lab experiments in an ice lab at JPL and in a rock mechanics lab at Columbia University. I'll start off with a brief overview of my thesis, which is tentatively titled Misunderstanding Ocean Worlds. It's motivated by and tends to enable the future exploration of the moon and the outer solar system, with a view towards extracting as much information as we can from remote sensing data and identifying the limitations of this data. This project or this thesis involves a three-pronged approach towards enabling target characterization and sample site selection for a future target, enabling analysis techniques, and developing new instrumentation which can help us better interpret the surfaces of these bodies. I have these three big picture science questions that have motivated individual projects within this work. And I started off with an initial focus on our moon, where I was looking at how can we characterize rocky planetary surfaces using reflected light. Can this be applied to icy surfaces, and what are its limitations? This led to the sensitivity and analysis of the Hapke photometric model, looking at phase coverage, topography, and image resolution to get a sense of how do they limit the interpretation of the moon and then subsequently icy satellites. While subsequently developing a balloon project for multispectral imaging of small bodies, I recognized the need for optical constants across a broad wavelength range, primarily for the outer solar system, which led me to pursue a cryogenic spectroscopy project where I looked at linking the optical, spectral, and the surface properties of various candidate materials for ocean worlds. This has allowed us to assess the limits of the 1.65 micron band in assessing ice crystallinity, determining the grain size and temperature dependence of water ice, as well as allowing us to update Europa's surface composition. Finally, under the NASA Sesame program with a view towards future exploration, we've been looking at the science capabilities of a tethered melt probe. And what I've been doing is looking at robustness studies for communication tethers, which are currently used in ice samples, in ice, and putting them for Europa's surface. Next slide, please. Now, in order to do this work, I've been able to develop a broad range of research techniques which are broadly applicable to the outer solar system. This obviously includes the Hapke photometric model for the sensitivity analysis, where I was able to learn image processing and figure out how to adapt these data sets, primarily initially from the moon, to the conditions that you'd get for the outer solar system and the data sets or the limited data sets that you get for the outer solar system. For the spectroscopy work, I was able to perform a UV visible and near infrared spectroscopy, first of all, by designing and fabricating a custom experimental setup that allows us to make grain size, composition, temperature, and radiation dependent spectra of samples. I was also able to learn and prepare samples, protocols for preparation of ice samples for these materials. Finally, for the rock mechanics and the ice mechanics work, we've been doing a lot of environmental tests looking at how these tethers would behave under different environmental conditions for these ocean worlds, be it long duration cold tests or as well as different shear and tensile tests. However, this is one part of my work. I spent a lot of time working on our moon itself during my master's thesis at the Indian Institute of Technology and the Indian Space Research Organization, where I first spent a little bit of time mapping impact craters on the lunar south pole, followed by modeling the microphysics of solar wind interactions with the lunar regolith, subsequently followed by spectral modeling of the M-Cube data sets from the Chandrayaan-1 mission. All of this has broadly allowed me to develop an expertise in the characterization of surface properties and the timescales for surface evolution. Next slide, please. And this feeds into my overall goal of broadly trying to improve our understanding of the surface physics and chemistry of the moon, ocean worlds, asteroids, and comets. I've left you with my list of broad research interests as well as images of certain bodies that I'm working on or developing proposals to work on. I'm interested in a broad range of research projects, primarily focused on techniques and looking at a broad range of jobs as well. So if you are hiring, I will be graduating at the end of the year, so feel free to get in touch, or if you just want any details about this work. Thank you for your time and stay safe.
All right. Thank you, Vishal. And I believe Jody's up next. Sorry. Lots of distractions here. All right. So whenever you're ready.
All right, great. All right, thanks everyone. Hello, my name is Jody Berdis. I'm in the 5th year of my PhD at New Mexico State University, and I'm also a NASA Jenkins Graduate Fellow and have the incredible opportunity to conduct research at JPL during the summers of my fellowship. So I study the composition of Europa's surface, and I am particularly interested in the differences between two types of water ice, crystalline and amorphous water ice. So they form under different environmental conditions, and so tracking their abundance and spatial distribution helps reveal how physical processes influence the surface, which can also aid in revealing the history of the surface. If you happen to find that amorphous dominates the surface water ice, you might gather that particle radiation and plumes influence the surface the most. On the other hand, if you find that crystalline dominates the surface water ice, you might gather that temperature and warm cryovolcanic activity influence the ice the most. And so their quantities can be determined both spectroscopically using a ground-based campaign that I led and laboratory data that I reduced, and also numerically through a code that I developed called Icicle. So there's a couple examples of that on the left side, the far left side of the screen. So the observed data seemed to indicate that there was much more amorphous. It seemed to win out. But the model data actually seemed to indicate that there was much more crystalline. So feel free to check out our paper. It's in the left center of the slide. It might be a little difficult to read, but it's Berdis et al. 2020, came out earlier this year. And so we discuss why the results from the observed data and the model data might differ, and we try to close the gap in between them. So if they really don't match, if these two different techniques are producing very different results, why might that be? So could it be some process that we've left out of our modeled calculation? So that's what we're looking into right now. So on the right-hand side of the slide is our current work. So we're using data from the Galileo spacecraft to perform a spectral mixture analysis or spectral unmixing, which refers to basically fitting the observed data to various combinations of known reference material spectra. This is at a couple locations at high resolution through the use of image cubes. So there's an example of that sort of in the top right corner there. And after performing some preliminary results, we also found that crystalline seemed to win this one out for the Galileo spacecraft data, which makes us wonder, was the original model correct? Or perhaps these two locations that we were looking at on the surface through the Galileo cubes were just flukes. So maybe they have some overactive geophysical processes that are occurring. But what's particularly strange is that we actually found zero amorphous in those data sets. And so that seems a little strange. We were expecting there to be a bit. And so right now we're actually working with a software called NV that's most often used for Earth-based remote sensing, but we're excited to see its application to Europa and merely start getting the spatial distribution of crystalline and amorphous ice within those image cubes that we're most interested in from Galileo, and hopefully get a better idea of how surface processes may influence the amount of crystalline and amorphous water ice present. Next slide. So before I flash up my contact information, I just wanted to provide a little more information about myself and sort of my research background and various other backgrounds that I've had. So I'm experienced in a wide range of programming languages. You can see there on the left side, in a diverse suite of analysis techniques, most notably for ground, space, and laboratory-based observations. But I've also done various modeling, including HAPI spectroscopic modeling and spectral unmixing. I served as executive secretary for 2 and almost 3 now NASA review panels, and have held numerous leadership roles in my department, listed here in the center there. You can read that on your own. And then finally, I'm dedicated to improving the quality of life in the workplace through diversity and inclusion initiatives, most notably as the group leader of my department's inclusive astronomy, and also participating in multiple equity, diversity, inclusion conferences, workshops, and efforts. And you can see all of those on the right-hand side there. Next slide. So I'm on the hunt for postdocs and jobs starting later in the fall. And so there's my, there's the link to my website for more information. The QR code links right to that website, and there's my contact email. And thank you all so much.
All right, great. Thank you, Jody. Okay, and Divya, if you're ready to go.
Uh,
Oh, wait, there you are.
Yep.
There we go.
yeah, hi there.
Okay,
Yeah, I'm
whenever
ready.
you're ready.
Sure. So I understand this is a lot of text on the slide, so I'm going to go through it just sort of piece by piece. So I'm a third and final year PhD student at UCL's Mullard Space Science Laboratory in south of London. And my bachelor's is in geology from the University of Rochester. So my PhD is focusing on planetary photogrammetry and applications of that for geology. So my background thus far, my PhD has been a lot of stereo image processing using various suites, including in-house software that's being currently, there we are, including software that is going to be integrated with the AIM stereo pipeline. And so with these 3D models that I've developed, and these are Mars focused, I've co-registered multi-resolution data sets, and I've also investigated novel quality assessment tools and workflows of these 3D data sets using 3D visualization. So the background here is one of my 3D mosaics of Gale Crater. So my background before my PhD was actually icy moons, and that's kind of where I want to pivot back. So some work that I did at the SETI Institute and JPL was using Cassini digital elevation models to measure impact craters on 4 icy bodies, 4 icy moons of Saturn, to investigate methods of estimating initial crater depths. So these are the initial depths of these craters before long-term viscous relaxation. So this can actually give us some insight into the geophysical evolution of these bodies when compared to models. So other forms of analysis from 3D, more Mars focused, have been 3D stratigraphy, actually from high-rise terrain data, and this has been using rover 3D visualization tools. So this is novel research that's being done with orbital data in a rover 3D data environment to actually study exposed layers in a channel. And also with 3D, also developing best practice for using 3D visualization with scientific data for public engagement, which is actually a really complex task. And my background is also in a lot of other forms of remote sensing. So with LiDAR, with different imaging sets, so Cassini, as well as Mars data sets, and to some extent rover as well. And then a lot of collaboration with radar studies, although not direct experience with radar analysis. So we have a paper coming out that's looking at subsurface ice on Mars, and then also experience with the NASA Academy in developing a mission concept for radar. And then some of my further background is in lab experiments, and I have other sort of mission team involvement, including with the ESA ExoMars PanCam team. Next slide, please. So focusing more on my icy body work, so in the upper right, I had to put the figures here. So that's just showing how I do stratigraphy from Mars orbital data. But on the bottom right is showing a Cassini digital elevation model. So this is just an example of one of hundreds of digital elevation models that I've performed measurements on for 4 different moons. So what I was doing was statistically comparing different methods in the literature, both for icy moons and also the moon and Mars, for estimating these initial crater depths, which is actually a really complex problem when we, of course, can't observe what these craters would have looked like initially. And so this is a publication that we're preparing. This is with Cynthia Phillips at JPL. And so with my future interests, having done this pivot into Mars and pivoting out of Mars again, is just sort of mixing the lessons learned with Mars, which is really that we need high fidelity matching of 2D and 3D imaging sets, which can also include spectral data. So really, ideally, I'd like to make new terrain models using new photogrammetry methods and hopefully improve global digital terrain models of icy bodies by comparing 3D data sets and combining them rigorously, and also performing assessment using 3D visualization. And then seeing what kind of geology we can do from there, where focused regions will be better contextualized in broader regions. So generally speaking, we can look at impact basins compared with smaller scale crater structure, or interesting structure on Galilean satellites, for example, and hopefully in synergy with models and lab experiments. And I'm particularly interested in impact experiments in ice. And next slide, please. And this is just my contact information. So there's my email and my website, and also the website of a conference that I'm hosting in about 3 weeks with a team of 2 people. So if you want to find out more about that, feel free to check that out. So thank you.
All right, thank you, Divya. All right, so that wraps up our presentations for this afternoon session.